Okay, so here any t here is mapped to z, which is e to the power 2 pi I t. And actually, if you just write this as a function in R2, this is cosine 2 pi t sine 2 pi t. So functions on the circle are actually functions of these gadgets, right? In other words, we may regard functions on S1 as a subring of functions on R, which are periodic with period 2 pi. Okay, so functions on the circle are nothing but functions on the real line, which are periodic with period 2 pi. In other words, I can just regard them as functions of cosine t and sine 2 pi t. Yeah. Another example. Consider the covering space from R2 into real projective plane, which I regard as so the quotient of S2 via this identification. Any point here is just identified, or maybe I should write it like this. So this is just real projective plane. Any point here is just identified with its antipodal, okay? And we obtain RP2. For example, let's consider polynomial functions on S2, polynomial functions on S2 regarding this as a subset of R3 can be thought as the polynomial ring on this three variables x, y, z. But then this is S2 is given by the equation x squared plus z squared minus 1 equals 0. So you have to just divide this by the ideal generated by this polynomial x squared plus y squared z squared minus 1. So this is the polynomial ring on ring of functions on S2. Okay. Here I'm not considering just continuous functions, but polynomial functions. So it's the quotient of this polynomial ring with this ideal, because this function is already 0 on S2. So I just regard this gadget as the 0 function. And the way you do this, you just divide this ring by this ideal. So this is the this is the fundamental construction in algebraic geometry. What about the ring of polynomial functions on this gadget? Well, here this action is just what? You identify a point with its antipodal. So if P is x, y, z, minus P is just minus x, minus y, minus z. So any function, let's say on RP2, of course, gives me a function here, f composition P, and this P just sends x, y, z to minus x minus y minus z. Therefore, this equation, so so this function here, f composition p x, y, z is the same as f of x, y, z, x, y, z. In other words, f of minus x minus y minus z is f of x, y, z, right? Yes. And this means what? F is a function so that it doesn't distinguish x, y, z from minus x minus y minus z. So what kind of object then this should be? Which functions, which polynomials doesn't distinguish this variables from these variables? They are just quadratic expressions, right? So the ring of polynomial functions on RP2 will contain, for example, the function x squared in it, because x squared, of this point and this point are the same. Y squared, z squared, x times y, y times z, and x times z. And actually, this thing just considered as a sub-algebra of this gadget is the ring of polynomial functions on RP2. Yani şunu söylüyoruz. RP2'nun üzerindeki fonksiyonları ben S2'da gördüğüm zaman onlar nasıl fonksiyonlar olacak? Bu iki noktayı birbirinden ayırt edemeyecek onlar. Dolayısıyla da hani square polinomial, kuadratik polinomlar olmaları lazım. Burada şöyle bir şey de aslında görüyoruz. Bu şeyin üzerinde yani benim diyelim ki bu deck transformation group işte Z2 bir tane sigma tarafından veriliyor. Sigma x, y, z is minus x, minus y, minus z. And my ring of functions, polynomial veya neyse diyeyim, bu A of RP2'yu ben şöyle görebilirim. Bu A of S2 ama bu sigma altında invariant olanlar, yani neyi kastediyorum? So these are functions so that F composition sigma is equal to F. So this action on the covering space gives me an action on the ring of functions, and this subring is the ring of invariant functions. Okay. Okay. Yani yukarıdaki and herhangi bir covering space aldığımda, so whenever I have a covering space like this, the ring of functions of y is considered as a function of function on x, and it is nothing but actually this thing, and then here I have this deck transformation group. Well, we said actually gamma, right? If it is a regular covering. So peki. Bunun ispatından bahsetmedim. Yani bahsetmeme gerek yok herhalde. Şeyde hani daha detaylı olarak yazdım ama yani fikir e, bu. Şurada bir fonksiyon aldığınız zaman o fonksiyonu ben burada görebilirim ve o fonksiyon e, yani P composition F e, covering transformation'lar altında invariant kalıyor ve aslında y'nin üzerindeki tüm fonksiyonlar da onlar. Yani buradaki bütün fonksiyonlar yukarıdan geliyor ama hangi fonksiyonlar onlar? Covering transformation'lar altında invariant kalanlar. So functions on y are just functions on x that are invariant under the action of gamma. Okay. Peki. Şimdi şeyden bahsedeyim. E, complex functions on C and surfaces. Şöyle bir tane complex domain alalım. Domain. So what we mean by domain is a open set, let's say, and F D to C an analytic function. Analitik fonksiyonlara holomorfik de diyoruz. Holomorfik. Yani bu ne demek? So F prime at any point so this limit exists at all z0 in D. Okay. Analitik fonksiyonlar bunlar. A function f, let's say d0 to c is called meromorphic. If f d0 to c is analytic, and d minus d0 is a finite set. So d0 is a subset of d, so that the difference is a finite set of points. Okay, so some points like this, and except these points, f is an analytic function. So example, for example, take d equals c and d0 to be just d minus 0, 1, and 2. So just 3 points. Then this function 1 over z plus 1 over z minus 1 plus, let's say, 5 over z minus 2 is a meromorphic function on D, on the complex plane. Okay. It is analytic at all points except 0, 1, and 2. Definition diyeyim şöyle. The set of all meromorphic functions on D is denoted as KD. Yani bu kitabın notasyonunda buna KD diyoruz. Yani ne demek KD? Meromorfik fonksiyonlardan oluşuyor. Her birisi D'nin sonunun noktasını çıkardığınızda geri kalan bölgede analitik olacak. Tabii ki o sonlu noktalar fonksiyondan fonksiyona değişir. Okay. Similarly, the set of all holomorphic functions veya analitik fonksiyonlar on D is denoted as OD. Remarks. OD is a ring. Yani değil mi? Bütün holomorfik fonksiyonlar bir ring oluşturuyor. İki holomorfik fonksiyonun toplamı holomorfik. Yani türevleri varsa iki fonksiyonun toplamı da türev var. Çarpımı da öyle. Meromorfikler daha fazlası. Meromorfikler bir field. KD is a field. Neden? Çünkü bir tane meromorfik fonksiyon aldığınızda hani zero'ları varsa da o da sonlu tane yani accumulation point'i olamaz. O yüzden de is a field, şöyle yazayım. Because any analytic function has at most finitely many zeros. Uh, bir dakika. Yani bu doğru değil ama ya. Evet. Evet. Yani burada niye böyle yazmışım? Acaba kompakt bir şey falan mı alıyoruz? Mesela sinüs değil mi? Sinüs x'in sonsuz tane zerosu var. O analitik bir fonksiyon. 1 bölü sinüs x de meromorfik bir fonksiyon. Acaba şey mi yapıyorduk burada? Tamam. Şey de almamışım, öyle bir şey de söylememişim. Herhalde onu atlamışız. Ah, yani belki meromorfik fonksiyonları şey diye söylemek lazım. Yani belki şey demek lazım. Is a finite set değil de discrete set demek lazım. Evet, evet. Şöyle yazarsak sorun discrete set. İşte ama şey dememek lazım. Hani sonlu tane zerosu o doğru laf değil. Function has has ya da because şöyle diyelim. The zero set. Any analytic function is discrete. Topolojik de discrete. Yani ne demek o şey? e, Her birisinin bir neighborhood'u var. O neighborhood'da bir tek kendisi var. Evet, evet, evet. Accumulation point'i yok. Zero'ların accumulation point'i yok. Şimdi şöyle bir dur bakayım. complex surface diyeyim. A complex surface sigma is a topological space so that for any point P in sigma, there is an open set containing P and the homeomorphism phi from U to V, where V is an open set in the complex plane. Where V is an open set, open subset, satisfying the following conditions. Whenever we have two bunlara coordinate patch diyeceğiz. Coordinate patches phi1 u1 v1 and phi2 u2 v2. The composition phi2 composition phi1 inverse from the image of phi1 to the image of phi2 is analytic, is holomorphic at all points. Yani şöyle bir şey. Bu surface şöyle iki tane open set var. U1, U2, this is sigma. And here I have phi1. This is mapped to the complex plane. And this is mapped to the complex plane, V2. When I look at the intersection here, that intersection is mapped to any subset like this, and this is also mapped to a subset like this. And here I have this composition map. These are homeomorphisms, therefore I can just go with the inverse of this map to the surface and then come back via the second map. So I obtain a map from this open set to this open set, and I require that this composition is a holomorphic map. It's an analytic map. If it is the case, then we say that this is a complex surface. Actually, one should be careful. Usually when we say complex surface, we take the images of these gadgets not in C but C2. So in the study of complex manifolds, surface means actually locally it is C2. Therefore, actually, surfaces are four-dimensional objects. But in this course, these gadgets will be just usual surfaces. So it's a two-dimensional object. Okay. Actually, they are called Riemann surfaces. Yeah. Da işte hani kompleks surface deyince genelde lokal olarak C2 olan objeler anlaşılıyor. Onlar da 4 boyutlu nesneler, 2 boyutlu değiller. Examples. Any open subset D of C is a complex surface. Burada yani bu bir tane phi alabilirsiniz. Şimdi yani bu stigmayı D'nin kendisi alırım. Bu map'i de işte yani bunu U alırım. V'yi de yine D alırım. Bunu da C'nin içinde. Bu map'i de identity map alırız. Yani Z'ye gider. Z'ye identity map. Hani bir tane coordinate patch yeterli olur. Bu herhangi bir open subset diyelim ki şeyin içinde. C'nin içinde. İkincisi Riemann sphere. Riemann sphere. Yani bu aslında bildiğimiz küre, başka bir şey değil. X, Y, Z. X squared, Y squared, Z squared is 1. Peki kompleks koordinatlar nasıl? Şöyle. Stereografik projection'ları düşüneceğiz. Ya şunu şey yazayım. X1, X2, X3 yazayım da notasyon evet karışacak çünkü X2, X3, X1, X2, X3. Projections are the following maps. So just consider this in R3. This is the North Pole. This is the South Pole. So the North Pole is just the point 0, 0, 1. This is the point 0, 0, -1. And we have two maps, phi n from S2 minus the North Pole, into the complex plane, and phi s S2 minus the North Pole to the complex plane. Phi n is defined this way. Whenever you choose a point here, you connect this point with the North Pole, you get a line. This line intersects the complex plane. Okay, this is the complex plane at a point here. Okay, at a point here. And of course, I can just regard complex plane as the XY plane. Okay, or okay, X1, X2 plane. And the other map is defined similarly. Whenever you have a point on the sphere, you just connect it with the south pole. So you get a line, and this line will just intersect the XY plane or X1, X2 plane at a point, and that point is just phi 2 of P. We can write down explicit expressions for the two maps. Let me just write down those maps. Phi n from UN being S2 minus the North Pole into R2, which we regard as the complex plane. So this map is just this. X1, X2, X3 is mapped to X1 divided by 1 minus X3, X2 divided by 1 minus X3. So this can be regarded as a point on the XY plane or X1, X2 plane, or I can regard it as a complex number. As a complex number, this is the real part, and this is the imaginary part, okay? Let me say this is the complex number Z, and then I have this map. It is given by a similar expression. The only difference is just instead of minus, I have plus. You see, this function is not defined at the point 0, 0, 1, right? When the third component is 1, it is not defined. So it is not defined at the North Pole. And this function is not defined at the South Pole, at which the X3 coordinate is -1. So this has a real part, this, and imaginary part, this gadget. And if you compare these two, you will see that this is just 1 over Z, okay? If this is the complex number Z, this is 1 over Z. Therefore, we have the following. We have the following. So I have from the Riemann sphere, we have map from U1 into V1, which is just the complex plane. And then I have U2. And so this is phi n, phi s. This is V2, which is just, again, the complex plane. And I have the transition function, which is just, so this function is phi s composition, phi n inverse, okay, from V1 into V2. And this map is just given by Z goes to 1 over Z. Okay, Z goes to 1 over Z. Buradan şunu da yazabiliriz aslında. S2, remember, is just U1 union U2, right? This is just S2 minus the North Pole. This is S2 minus the South Pole. So this point misses the North Pole, but this one has the North Pole, and vice versa. So the union is just S2. And via this homeomorphisms, U1 and V1 are actually identified. U1 is just a copy of the complex plane. So I can just write it like this. U2 is a copy of the complex plane, but actually they are, regarded as disjoint copies. Let me just, indicate that by putting disjoint union. But then we do the following. Any complex number here is identified with a complex number here, except 0. And how is the identification? So this Z here is identified with 1 over Z in the other complex plane when Z is not 0, okay? So you just have 2 copies of the complex plane. You just glue them so that the 0 of one complex plane goes to the infinity in the other complex plane. So one-dimensional picture maybe is more illuminating. So you have, let's say, okay, 2 copies of the, suppose, these are the complex lines. You just glue every point here with every point here, except the zeros, so that this Z goes to 1 over Z. Bu ne demek? Yani when you go to infinity, Z goes to infinity, so 1 over Z goes to 0. Therefore, you just bend these arms so that they are mapped to 0. So this is, something like this. This is one complex plane. Okay. And the other complex plane is like this. Its 0 is over here, and these are the arms going to infinity. So you have 2 complex plane. You just, bend it so that the arms going to infinity goes to 0 here, and the same picture for the other one. Yani bir boyutta daha iyi anlaşılıyor ama aynı şey zaten bir boyutta da geçerli. Peki, complex surface'lar bunlar. Tabii daha bir sürü var. Şimdi okay. Functions on complex surfaces. Aslında bunlar dediğim gibi Riemann surface deniyor bunlara. Riemann surfaces. Şey olarak holomorphic function kastettiğimiz şey şu olacak. Yani bir tane fonksiyon aldığımızda herhangi bir koordinat sistemi aldığımız zaman, yani bir tane U varsa ve şeyin içinde bu U'da bir tane koordinat sistemine karşılık geliyorsa V'ye, o da C'nin içinde. Şimdi buradan buraya giden fonksiyonu ben U'ya kısıtladığımda U'yu da bu V ile aynı gördüğüm zaman, o zaman V'den buraya giden bir fonksiyon gibi görebilirim. Yani nedir o? Bu fonksiyonun inverse ile git, ondan sonra da F ile git. Dolayısıyla kompleks düzlemin bir open subsetinden C'ye gidiyorum. Eğer bu fonksiyon holomorfikse o zaman F'e de işte holomorfik diyeceğiz. Meromorfikse F'e de meromorfik diyeceğiz. So a function f from is called holomorphic if f is holomorphic on each coordinate patch. Similarly, a function is meromorphic if it is meromorphic on each coordinate patch. Yani şöyle bir resim çizeyim. So here I have my surface, let's say, and we have a function f to complex plane. And what I do, around each point here, I have a coordinate patch, and this is mapped to some open set V in the complex plane. I know that there's a homeomorphism. So what I can do, I can just look at this composition. Since this is an homeomorphism, I can go with the inverse of this map and then compose that with F, and we obtain a map from an open set in C to C. So this is the map from an open set in the complex plane to C. And I can ask if this function is analytic or meromorphic. So if this is analytic for each choice of this coordinate patch, then we will call this analytic. And if these are all meromorphic, then I will call this function meromorphic. Yani bu surface'larda çalışırken yaptığımız şey her zaman bir noktadaysam o noktanın bir civarını ben kompleks düzlemdeki bir open set olarak görüyorum. Bu fonksiyonu da bu open set'te tanımlı olarak görebilirim. Bu fonksiyonun yardımıyla, koordinat patch'in yardımıyla bu fonksiyona bakıyorum. Open bir setten C'ye gidiyor. Bu fonksiyon analitikse her bir koordinat patch için o zaman buna da analitik diyorum. F'e de analitik diyorum. Eğer meromorfikse meromorfik diyorum. Mesela bir örnek yapalım. Örnek yapmayalım ya da. Evet, zamanı doldurmuşum. Bir dahaki ders bir iki örnek vereceğim. Ondan sonra da şeye devam ederiz. Fikir kaydı durdurayım da. Yani